In this video, we're going to continue talking about random variables and probability distributions, specifically mean and standard deviation of a random variable. Now, as far as means and standard deviations of probability distributions go, the mean value of a random variable x, denoted by mu sub x, describes where the probability distribution of x is centered. And the standard deviation of a random variable x, denoted by sigma sub x, describes variability in the probability distribution. Mean is sometimes referred to as the expected value, denoted by E of x. So we have mu sub x equals the sum of x times p. Now variance is calculated using sigma squared equals the sum of x minus mu sub x quantity squared times p. The standard deviation is the square root of the variance. So in a previous problem, we had talked about cats and dogs in Wolf City. We're going to go back and revisit that problem. So again, we're going to let x equal the number of dogs and cats in the randomly selected household in Wolf City. So we want to know, what is the mean number of pets per household in Wolf City? So we're going to first multiply each x value times its corresponding probability, which is given by x times the probability of x. Next, we're going to find the sum of these values. So our mu sub x is going to be 1.51 pets. So what is the standard deviation of the number of pets per household in Wolf City? Well, first, we're going to find the deviation of each x value from the mean. Then square these deviations. Then we're going to multiply by the corresponding probability and then add these values. So we have our sigma sub x squared equals 0 minus 1.51 quantity squared times 0.26. So remember, this is our x, this is our mu sub x quantity squared times the probability of 0. You'll notice that that happens at each piece. So when we sum all those together, that gives us our 1.7499. This is the variance. So we're going to take the square root of that, and that's going to give us our standard deviation sub x, which is 1.323 pets. Now, mean and variance for continuous random variables. So if we talk about continuous probability distributions for our mu sub x and our sigma sub x, it can be defined and computed using methods from calculus. So the mean value, or mu sub x, locates the center of the continuous distribution. The standard deviation, or sigma sub x, measures the extent to which the continuous distribution spreads out around mu sub x. Let's look at an example of these. So a company receives concrete of a certain type from two different suppliers. So we're going to let x equal the compression strength of a randomly selected batch from supplier 1. And we're going to let y equal the compression strength of a randomly selected batch from supplier 2. Now suppose that mu sub x equals 4,650 pounds per square inch, and that our sigma sub x equals 200 pounds per square inch. And our mu sub y equals 4,500 pounds per square inch, and our sigma sub y equals 275 pounds per square inch. So if we look at how this might distribute out, here's our mu sub x, and here is our mu sub y. Notice that the first supplier is preferred to the second, both in terms of mean value and variability. Let's go back to Wolf City, but this time let's talk about the grocery. So Wolf City Grocery had a total of 14 employees. The following are the monthly salaries of all of the employees. The mean and the standard deviation of the monthly salaries are going to be mu sub x equals 1,700 and sigma sub x is going to equal $603.56. Now suppose business is really good, so the manager gives everyone a $100 raise per month. The new mean and standard deviation would be mu sub x equals $1,800 and sigma sub x equals $603.56. What happened to the means? That's right, they all increased by the $100. What happened to the standard deviations? Yeah, they stayed the same. So let's graph box plots of these monthly salaries to see what happens to the distributions. So we see that the distribution just shifts to the right 100 units, but the spread is the same. So what would happen to the mean and standard deviation if we had to deduct $100 from everyone's salary because of business being bad? What do you think? Did you say it would just shift it to the left 100? Because that's what would happen. Now, suppose that the manager gives everyone a 20% raise. So here, the new mean and standard deviation would be as follows. Our mu sub x would be $2,040, and our sigma sub x would be $724.27. So notice here that both the mean and standard deviations increased by 120%. We multiplied by 1.2. So let's graph these box plots of the monthly salaries to see what happened to the distributions. So here we have our original salaries, and our salaries plus the $100, and now we have this next situation of a 20% raise. So notice that multiplying by a constant stretches the distribution, thus changing the standard deviation. Let's talk about the mean and standard deviation of linear functions. If x is a random variable with a mean of mu sub x and a standard deviation of sigma sub x, and a and b are numerical constants, and the random variable y is defined by y equals a plus bx, and mu sub y equals mu sub a plus bx, which equals a plus b times mu sub x, and the sigma squared of y, or sub y rather, equals sigma sub a plus bx squared, or sigma squared sub a plus bx. That would give us b squared times the sigma squared sub x, or the sigma y sub y equals the absolute value of b times the sigma of sub x. Let's look at an example. Now, consider the chance experiment in which a customer of a propane gas company is randomly selected. And we're going to let X be the number of gallons required to fill a propane tank. So suppose that the mean and standard deviation is 318 gallons and 42 gallons, respectively. Now the company is considering the pricing model of a service charge of $50 plus $1.80 per gallon. So we're going to let y be the random variable of the amount billed. So we want to know, what is the equation for y? You should have said that y equals 50 plus 1.8x, right? We have our service charge of $50 plus $1.80 per gallon. Now, what are the mean and standard deviation for the amount billed? Well, our mu sub y, or our mean, is 50 plus 1.8 times 318 gallons, which is $622.40. And our standard deviation is going to be 1.8 times 42, which is $75.60. Let's look at another example. Now suppose we're going to play a game called Statland, and players spin the two spinners below and move the sum of the two numbers. So here are the mean and standard deviations for each spinner. So we're going to list all of the possible sums of A plus B. So we can get 2, 3, 4, 5, 3, 4, 5, 6, 4, 5, 6, 7, 5, 6, 7, 8, 6, 7, 8, 9, 7, 8, 9, 10. So we're going to find the mean and standard deviation for these sums. So we're going to take the mu of sub A plus B, and that's going to be a 6. And the standard deviation sub A plus B is 2.041. So notice that the mean of the sums is the sum of the means. Well, how are the standard deviations related? Not sure. Let's think about it and return in just a few minutes. Let's list all the possibilities of the differences of B minus A. Here we have 0, -1, -2, and -3. And 1, 0, -1, and -2. And 2, 1, 0, and -1. 3, 2, 1, and 0. And 4, 3, 2, and 1. And 5, 4, 3, and 2. So now we're going to find the mean and standard deviation for these differences. So I want you to go ahead and do that. So push pause, and when you're done, push play, and let's see if you were right. So you should have gotten that the mean of B minus A is 1, and that the standard deviation of B minus A is 2.041. Notice that the mean of the differences is the difference of the means. But wow, this is the same value as the standard deviation of the sums. So how do we find the standard deviation for the sums or differences? Now, if x sub 1, x sub 2, all the way through x sub n are random variables with means of mu sub 1, mu sub 2, all the way to mu sub n, and variances of sigma sub 1 squared and sigma sub 2 squared, all the way to sigma sub n squared, respectively, and we can say that y equals a sub 1 times x sub 1 plus a sub 2 times x sub 2, all the way to a sub n times x sub n, then we're able to say that the sum of y the sum of the mean of sub y is a sub 1 times the mean of x sub 1 plus a sub 2 times the mean of x sub 2 all the way to a sub n times the mean of x sub n. Now, this result is true regardless of whether the x's are independent. Our sigma sub y, or our standard deviations, is going to be the square root of our a sub 1 squared times our sigma sub x sub 1 squared plus a sub 2 squared times sigma sub x sub 2 squared, all added all the way up to a sub n squared times the sigma of x sub n squared. This result is only true if the x's are independent. Let's look at an example. So a commuter airline flies small planes between St. Louis Obispo and San Francisco. For small planes, the baggage weight is a concern. So suppose it is known that the variable x equals the weight in pounds of baggage checked by a randomly selected passenger, and it has a mean and standard deviation of 42 and 16, respectively. Consider a flight on which 10 passengers, all traveling alone, are flying. The total weight of checked baggage, y, is going to be x of 1 plus x of 2 all the way to x of 10. So what is the mean total weight of the checked baggage? Well, it should be our mu sub 1 plus mu sub 2 all the way to mu sub 10. So 42 plus 42 plus 42, so 420 pounds. Well, what is the standard deviation of the total weight of the checked baggage? Now, since the 10 passengers are all traveling alone, it's reasonable to think that the 10 baggage weights are unrelated and therefore independent. So we can take our mu sub x squared is going to be our sigma of x1 quantity squared plus our sigma of x2 quantity squared added all the way up to our sigma of x10 squared. So remember, that's our sigma x is 16. So 16 squared plus 16 squared plus 16 squared, all the way up to our 10th passenger, we'll have that 16 squared. And that's going to come out to 2,560 pounds. Now to find the standard deviation, we're going to take the square root of this value because that was just the variance. Take the square root and we're going to get 50.596 pounds.